For years, the recipe for smarter AI was simple: train a bigger model on more data with more GPUs. That still matters, but it is no longer the whole story. The new frontier is test-time compute, spending more computation after the prompt arrives, while the model is answering. A normal model answers like a reflex. It reads the prompt, predicts tokens, and commits. A reasoning model spends extra tokens exploring the problem. It tries partial solutions. It checks them. It may backtrack. Then it answers. Training makes the model capable. Test-time compute decides how hard it tries. So let's break down what test-time compute is, why it works, why it gets expensive, and why it may be the most important scaling law after the transformer. Start with the old pattern. You give a model a prompt. The model runs over the context, then generates an answer token by token. For many tasks, that is exactly what you want. Summarize an email, rewrite a paragraph, answer a simple question. Hard reasoning tasks are different. Math proofs, debugging, planning, competitive programming, scientific questions, these often require search. Humans know this intuitively. If a problem is easy, you answer from memory. If it is hard, you use scratch paper. You try a path, you notice it fails. You restart. Reasoning models bring that pattern into inference. The model generates intermediate reasoning tokens, sometimes hidden, sometimes visible, and those tokens become a workspace. The workspace is not magic. It is computation. Every extra thinking token costs time, memory, bandwidth, and money. When people say a model is thinking, it can sound mysterious. Operationally, a lot of it comes down to tokens. A standard answer might use a few hundred output tokens. A reasoning answer might use thousands. The model writes assumptions, decomposes the task, derives intermediate results, and tests whether a path makes sense. Those extra tokens matter because language models are autoregressive. Each new token changes the context for the next token. A reasoning trace gives the model a richer state to condition on. That is why chain of thought prompting worked. Asking a model to think step by step gave it room to represent intermediate structure instead of jumping straight to a conclusion. Modern reasoning systems go further: multiple paths, verifiers, tool calls, and variable compute budgets. Test-time compute is not one trick. It is a family of ways to buy better answers with more inference work. The simplest way to spend more compute is parallel sampling. Instead of asking the model once, ask it several times. Let it generate different reasoning paths. Then choose the most common answer, or the answer with the strongest supporting logic. This is self-consistency. One chain of thought can be brittle. 10 independent chains are less brittle. If several arrive at the same answer through different routes, that answer is more likely to be right. But parallel sampling has limits. It is like asking 10 people to solve the same problem in separate rooms, then taking a vote. Nobody learns from the failed attempts. Sequential search is more powerful for hard problems. The model explores a path, evaluates it, revises it, and continues. That is closer to a tree search. Branch, score, prune, branch again. A chain is one path. A tree is a space of possible solutions. Once you generate multiple reasoning paths, you need a way to choose between them. The cheapest version is an outcome check. Did the final answer match the expected result? For math, code, and formal logic, this can be powerful. If code passes tests, that tells you something. If an equation balances, that tells you something. But outcome checks have a blind spot. A model can use broken reasoning and still land on the right answer by luck. Or it can make a bad assumption halfway through and still sound convincing. That is where process evaluation comes in. An outcome reward model scores the final answer. A process reward model scores the steps. Was this move valid? Did this inference follow? Did this branch introduce an error? For a reasoning system, That changes the search. The model can prune weak steps earlier and spend compute where it is more likely to pay off. This is why verifiable domains moved fastest. Math has answers, code has tests, logic has constraints. If the environment can tell you when you are wrong, search becomes much more useful. Here is the practical problem. You cannot spend maximum reasoning compute on every query. Most prompts are not hard enough to justify it. If someone asks for a short email rewrite, deep reasoning is wasteful. The extra latency hurts the experience, and the extra tokens burn money for almost no gain. So the real product pattern is adaptive compute. First, estimate how hard the task is, then send it down the right path. Easy prompt? Use a fast model and a small token budget. Hard prompt? Give it a larger budget. Sample multiple paths. Call tools. Run code. Use a verifier. Continue searching until confidence is high enough. The system should not have one fixed intelligence setting. It should have a compute policy, cheap lane, reasoning lane, and escalation when verification fails. The future is dynamic inference, different budgets for different problems. The most important thing about reasoning models is that the capability did not stay locked inside one lab. Open models showed that reasoning behavior can be transferred. The basic idea is distillation. Take a large reasoning model, have it generate high-quality reasoning traces. Then train a smaller model on those traces. The smaller model does not just learn final answers, it learns the style of problem-solving, decomposing, checking, revising, and continuing when the first attempt fails. DeepSeek R1 made this pattern impossible to ignore. It showed that reinforcement learning and distillation could produce strong open reasoning models, including smaller versions that developers could actually run. That matters for local AI. A smaller, distilled model may not beat the frontier on every benchmark, but if it can reason well enough on your hardware, with your data private, at predictable cost, that is a different kind of value. Now the caution: longer reasoning is not automatically better reasoning. A model can spend thousands of tokens rationalizing a wrong answer. It can explore a bad branch in impressive detail. It can produce a reasoning trace that sounds rigorous but contains a subtle false step. There is also the cost problem. Test time compute shifts expense from training into inference. That can be great for rare, high-value tasks. It is harder for high-volume products where every extra second and token matters. And there is domain mismatch. In code, you can run tests. In math, you can often verify the result. In open-ended human domains, the verifier is much weaker. The model may sound more thoughtful without being more correct. So the lesson is not, always make the model think longer. The lesson is this: use extra reasoning only where search and verification actually help. Test time compute is a new scaling axis. For years, the industry mostly scaled intelligence before deployment. Bigger datasets, bigger models, bigger training runs. Now, we are also scaling intelligence at inference time. The model receives a problem, then spends a variable amount of compute trying to solve it. That is the shift. The model is not just retrieving what it knows, it is searching through possible answers. It is using tokens as scratch space. It is using verifiers and reward signals to decide which paths are worth continuing. This makes AI more capable, but also more complicated. The central engineering question becomes, how much thinking is this problem worth? Too little, and the model answers reflexively. Too much, and you waste latency and money. The winners will be systems that allocate compute intelligently, fast when the problem is easy, deliberate when the problem is hard, and skeptical when the answer can be checked. That is why test time compute matters. It turns inference from a single pass into a strategy. If you are building with AI, ask a different question. Not just which model is smartest. Ask, Which tasks deserve more thinking, and how will I know when the answer is good enough? That is the test time compute problem. Subscribe for more deep dives into how modern AI actually works.